Okay, let's try to get started then, I guess. So thanks, welcome everyone, and big thank you for coming, Alhussein. And thank you for the organizers once again for setting up all of this, especially in this kind of difficult COVID times. It's really nice that so many people from different places can come, especially Alhussein, who's across the street from me in the same company. So this is going to be a nice introduction. So we actually don't work in the same group, but Alhussein has been working on the pure mathematical side of deep learning and basically using deep learning for mathematics, which I think is a very promising and interesting new direction. And I think I'll let you get started on what you've done on this.
Cool. Thanks, Jonas. So thanks for the invitation. I'll be talking about proving inequalities with deep learning, which is joint work with Mateusz, Malinowski, Hamza Fawzi, and Omar Fawzi. Okay, so in the recent years, we all know that there's been huge improvements in many areas in machine learning, especially perceptual tasks, such as image classification, image captioning, image generation, speech recognition, playing complex games like StarCraft, and these fields have just seen a huge improvements in their performance. For example, in image classification, we've seen now machine learning models that are able to achieve the performance that is on par with what humans are able to do on a complex data set like ImageNet, which is just amazing. So today in my talk, I'd like to depart a bit from perceptual tasks and consider tasks that involve reasoning. So in particular, what I'll be talking about is basically mathematical proving, which I think is a task that is of different nature than these perceptual tasks, and where we have many more challenges. And I think this is something that is going to be one of the next very important challenges for deep learning, to attack such tasks that do involve reasoning. So the starting point is basically a simple observation that the networks that are just very impressive in perceptual tasks, such as image classification, for example, there are many evidences basically that suggest that they don't perform any reasoning, but rather they are closer to pattern matching than reasoning. So like evidence behind this is basically, for example, the existence of adversarial perturbations or universal adversarial perturbations, where you can add a single pattern here to all images. So this single pattern, you add it to all images, and suddenly all images become classified as dogs, basically, because the pattern is very much closer to the pattern of a dog, for example. So you get classified completely as a dog, no matter what your original image is, basically, even though the original image and the perturbed images are very close to each other. So these classifiers are not really classifying images because, you know, like they're saying, okay, I have an animal with this, you know, like with this characteristic, and therefore it's something much more, I think, closer to pattern matching, basically. So as I said, I want to basically talk to you about mathematical proving and one instance of mathematical proving. And I think there are two things that are really exciting for me about mathematical proving. First is, and working in mathematics in general, first that it involves reasoning. I mean, mathematics is the pinnacle of reasoning. And also one of the very nice properties is that it gives you, like, it is verifiable, in the sense that if a machine learning system basically gives you a proof, that you can take the output of the machine learning system, you know, like this proof, and then check it for yourself to see whether it makes actually sense or it doesn't make sense. In other perceptual tasks, this is a very hard thing to verify, right? Because of the nature of the task, it's very hard basically to take what the network outputs and then verify it basically automatically. Okay. So okay, so mathematical proving. We want to prove or disprove statements starting from some axioms and using well-defined inference rules. Okay, so what we'll be considering is basically starting from axioms, and then from the axioms deriving lemmas, and then from these lemmas deriving other lemmas, and so on, till we get to the final theorem. And to go from one lemma to another lemma, this is what we call an inference rule. Okay, so this allows you, basically, these are like rules that are pre-specified, and this allows you to get from basically one lemma to the next lemma. Okay. As I said, the correctness of a proof can be verified mechanically. If somebody gives you a proof and claims that this is a correct proof, then you can check it for yourself. So this is a nice property. And the hard part of basically proving is actually coming up with which lemma to derive. Obviously, this is a hard search problem. And this is where we'll try to use machine learning, and I'll be describing some of the challenges behind this. Okay. So just maybe to give an example, let's say we want to prove or disprove Cauchy-Schwarz inequality. What we'll be doing is try to give it to a neural network. I mean, the general picture is to give it to a neural network, and then the neural network would not only tell you that it's true, okay, that the Cauchy-Schwarz inequality is true, but it also gives you a certificate that it's true. So basically, you can check it for yourself. And obviously, like mathematical proving is not something that is only like interesting from a reasoning, like to analyze basically whether neural networks can do reasoning and so on, but rather actually it has a lot of applications, in particular in program verification, verification of robot trajectories and so on. So it's actually something that is of very much practical use. Okay, so more specifically, the language that we'll be using is basically polynomials. Okay, so we'll be using multivariate polynomials, things like this. Okay, and the reason why we basically chose the language of polynomials is that they are extremely expressive in the sense that like any continuous function can be uniformly approximated as closely as desired by a polynomial function, but it also has, I think, a lot of applications that are like in control theory, robotics, program verification, and so on. And I'll give a few examples how we can model some of the problems that don't look like they're related to polynomials at all with actually this language of polynomials. Okay, so the first example is basically you can model combinatorial problems using polynomials. So as an example of a combinatorial problem, you can consider the stable set problem, or it's also called the independent set problem, which is basically the following. So you're given a graph, okay, and then the stable set of this graph is basically a subset of vertices, such that for every two vertices in this set, there is no edge connecting the two. Okay, so that's basically a stable set. And then the stable set problem corresponds to finding the largest stable set in this graph. So maybe to give an example, the largest stable set in this graph is basically of size 2, because if you take any other node here, then you will basically not satisfy the assumption or like this constraint, because basically there will be an edge between this one and this one here. Okay. So the larger stable set of this graph is basically 2, levels of cardinality 2. And if you consider the complete graph, obviously the larger stable set of the complete graph is basically of size 1, because if you take any other node here, obviously you'll be connected to this one. So you this constraint is not satisfied. Okay. Okay. So how do you frame this with polynomials? So let's say that your graph is of size n. So you want to find the largest stable set, so it's a maximization problem, and x here is going to define basically it's going to be the characteristic vector of the characteristic function of whether each node belongs or no to the set S, okay, to the optimal set S. So it's either going to be 0 or 1, okay, depending on whether you choose it or no, this node. And then you're trying to basically find the set of largest cardinality, and the cardinality is just the sum of xi's, subject to you don't want to have any edge between two nodes from in the set S, right? So you will basically put that xij is equal to 0 for all ij that have an edge connecting these two. And also you'll say basically that xi squared is equal to xi. So right, because you want xi to be in 0, 1. Okay. So in this way you frame the problem completely as a polynomial system of equations. And then what we'll be interested in particular in this talk, is going to be basically to prove that there is no stable set that has cardinality larger than gamma. Okay, so there are basically two sides to this. You can either derive an upper bound or a lower bound. So deriving a lower bound consists in finding a feasible solution And deriving an upper bound is the thing that does require indeed a proof, like, so like the thing that we'll be focusing on is basically the side that is harder, basically that there is no stable set that has cardinality larger than a certain gamma. Okay. So obviously there are many other problems that you can model using using polynomials. So these are just a few from IMO, for example. So these are things to prove, and they don't need any conversion. So these are naturally occurring in this language, except this one where you have to basically multiply basically these denominators to make sure that everything is polynomials on the left-hand side. And also this problem, for example, where you geometry problems where you have things that you want to prove on triangles, for example, where you have ABC forming a triangle, and then you want to prove some inequality on the area. Okay. And you can again convert this into a polynomial system of equations by saying an acute triangle, I can write it as a set of 3 equations, and the area I can also express it in terms of this ABC. And so what you get at the end of the day is a polynomial system of equations. Okay, so if we basically try to generalize the problem, so our problem is basically to prove that some polynomial P is non-negative for all x, basically that satisfies G1 of x is non-negative and Gk of x is non-negative. Okay, so that's the problem that's given to you, and then your goal is basically to try to find a proof for this. Okay. As I said, we need to basically define the inference rules, and the inference rules that we'll be using is basically that if you have a polynomial that is non-negative and you multiply it by one of these GIs that are non-negative by definition, then you also get a new polynomial, GI times H, generally of higher degree, that is non-negative, right? And if you have also, that's the first inference rule. The second inference rule is that if you have HI that is non-negative and you do a non-negative linear combinations of the HIs for any non-negative, for any lambda i's basically, then you get also a new polynomial that is non-negative. Okay. So, and then, as I said, the proof that P is non-negative corresponds basically to the composition of inference rules, which yields exactly the polynomial P. That's exactly what you want to find, what inference rules to combine together in such a way to get exactly this polynomial P that you care about eventually. Okay. Okay, so let's have a look at an example, again, from the stable set problem. So as I've said, the largest stable set or the largest independent set of a complete graph is of size 1. Okay, so so you can rewrite the problem that I just could be like in some previous slides. This is the problem of the largest stable set. Or like the constraints of the problem of the largest stable set, and then you want to prove basically that sum of xi's is less than 1. So remember that we want to derive upper bounds and not lower bounds on sum of xi's, okay? Because we want to prove that there is no stable set larger than something. So how do we go about doing this? So we basically start with this inequality, which basically tells us just that x1 is less than 1. So we know that all xi's are between 0 and 1, so that's something we know already, so we can take from here. And then we're going to multiply this first inequality with 1 minus x2, okay, which is one of our GIs, right? Which we're going to reduce using xi xj is equal to 0. Okay, so this is again going to give us that 1 minus x1 minus x2 is non-negative. And then we're going to take again this this polynomial, which we have just proven to be non-negative. We're going to multiply it by one of the GIs, okay? And by definition, this is non-negative. We're going to reduce based on the equality here, and so on and so forth, till we basically get that 1 minus sum of xi's is all non-negative, okay? So this proves basically that the larger stable set of a complete graph is less than or equal to 1, and therefore is equal to 1. Okay, so you can see here that at this, like in this proof, the polynomials basically at each step are of degree less than or equal to 2, basically. So it's a relatively simple proof, basically, in terms of the degree of the polynomials. Okay. Okay, so how do we basically find this proof, right? So how do we find this path basically that I just showed that starts from this 1 minus x1 till this 1 minus sum of xi's basically is bigger than 0. So so what we are going to use is basically reinforcement learning, and we're going to model basically the task of finding this dynamic proof as an interaction between an agent and an environment. Okay, so the agent is going to propose some action, okay, and then the environment is just going to give you some reward and basically update the set of lemmas that you have proven already. Okay, so like add this new action to the set of lemmas that you have already. Okay, we'll come to what is the reward and so on in a minute. So the goal is basically to maximize the sum of future rewards. Okay, so the sum of future rewards is basically how good you are at finding this proof that you care about. And so we'll be using here a relatively simple technique for reinforcement learning, which is called Q-learning. And basically the goal is to learn a function that calculates the quality of the state-action combination. So the Q value function here is basically takes as input a state and an action. Okay, so a state corresponds to basically all the lemmas that you have proven so far, and an action is going to be basically a new lemma that you have just found. And then it's basically going to tell you how good is this action, how good is it to take this action starting from this state. Okay. So, so in the beginning of the algorithm, Q is basically initialized randomly, and then we're going to do some updates to Q. So that's the process of learning through Bellman optimality equations, basically. And then after learning, we can extract a policy from this Q by basically taking the action that leads to the largest Q value function, basically. Okay, so a policy is basically a function that maps states to actions. Okay, and you can just like take you can derive it from Q by basically looking at all the different actions at a particular state and then just taking the one that has the largest Q. Okay. Okay, so now this application is actually quite difficult in the sense that the number of possible states is very large. So just to give you an example, the number of possible states in computer Go, for example, which is the number of possible board positions, is around 10 to the power 170. So in our case, the number of states is actually infinite, right? Because remember that the inference rules that we have are actually continuous in the sense that like we can put any coefficient, these lambda i's, you can put any of these. So just go back to this slide. Yeah. So you remember we have this this inference rules. If you have basically a set of hi's that are non-negative, then you can combine them with any non-negative linear combination, and you also get some polynomial that is non-negative. So essentially, the number of states that you have is actually infinite. Okay. The idea is basically to use, so obviously we'll not be able to tabulate all possible states and actions. So instead we'll use a value function approximation. So we're going to parameterize our Q value function using a neural network. Okay, and that's basically it. So basically we're going to take as input the state and action, and the neural network is going to tell us basically how good is this state and action. So to give you like some grounding in other in games, in Atari, for example, so the state would correspond to the pixel space basically of the game, and then the action would correspond to basically turn like go right, go left, go up, go down, for example. The number of actions is much larger than this, and also the number of states is much larger.
We just had a question in the chat, which you might want to answer now. This is easier. Elena asked, what are the Bellman optimality conditions? If you just elaborate quickly.
Yeah, so this is basically, I mean, I don't have much time to go in detail about this, unfortunately, but it's basically using dynamic programming to update your Q value function. So basically, to say that if I derived you know, like the q-value functions at different states are related with some equation. So basically, the q-value function at a certain state is, you know, like a reward plus the q-value function in another state. Okay, so you can basically try to you know, like try to write basically relations between the q-value functions at different states, and then you can try to solve these basically. And basically, it's the same idea behind the dynamic programming. But that's really the underlying idea behind reinforcement learning. So, and that's, I think, something that's really one has to look at in detail. I cannot really explain it in just a few minutes, but that's basically the rough idea. Okay, so so yeah, as I said, we have basically the agent, which is the prover, and so the state that we are at currently is basically characterized by the memory. The memory basically is all the elements that I have proven so far, as well as the axioms. Okay, so that basically contains all the lemmas that are non-negative, and also the equalities that I have. So, for example, xi squared is equal to xi, and so on. And then the function that I want to basically upper bound. Okay, so that would be the sum of xi's, for example. Okay, and then yeah, at each step, as I said, you're going to take an action. Okay, so and the action is going to be basically you're going to look at the lemmas that you have proven so far, and then you're going to multiply one of these by 1 minus xi, or like you're going to multiply them by one of the gi's that you have. Okay, so then you're going to update your memory so that basically you get a new polynomial that you have proven to be non-negative. That's what the environment is doing, and then you're going to give basically a reward. Okay. So that's basically how it goes. Basically, you start with an action, and then you basically update your you add your action to the memory, and then you basically get some reward. Okay. So then basically you do several iterations of this, and that's what we call the episode length. So we use deep Q networks to train the prover, as I said. So basically that's Q learning using neural network function approximation. And then there are basically two very important ingredients to make this work. You need to basically use dense and unsupervised rewards. And also you need to incorporate some important symmetries in the network itself. Okay. Wow, okay, I'm well behind. Okay, so so the first idea is basically to use dense rewards rather than sparse rewards. So you could basically try to give a reward at the end of each episode, just, you know, like a positive reward if you manage to get the proof, and otherwise you just give a 0 reward, right? So there are two problems associated to this sparse reward. The first one is basically that you need supervision, so you need basically to know what's the optimal, what's the largest stable set in your training data, and that's not something we wanted to have. So basically we want to have things in a completely unsupervised way. And the second problem is that sparse rewards makes learning very difficult, right? So you get a reward just at the end, at the very end of the episode. So that's why we used instead dense and unsupervised rewards. So we actually give now a reward at each step, and the reward that we're giving is basically how much does your bound improves. Right, so so you just chose an action, and then you can basically now compute how much does your bound improve when you have versus what you had before choosing this action, and then take the difference between the two. Okay, so if you go a bit more in detail, remember, for example, that f was basically the sum of xi's in this larger stable set problem. So so we want to find basically the smallest upper bound on this f. Okay, so subject to basically this gamma t minus f is non-negative. So the idea is to try to combine all the elements that you have in your memory. So all the lemmas that you have in your memory, you try to combine them in a linear way, in such a way that basically gamma t provides an upper bound to f. Okay, so at each step of my reinforcement learning, I'm basically asking, okay, now I have these elements in the memory. What's the best bound I can get from these? This is gamma t, and then I store this gamma t, and then I can basically take the difference between these gamma t's and the previous gamma t, and this gives you basically how are you doing basically in terms of this new action. Okay. The second thing you need to do in order to make this work is basically to incorporate symmetries. So there are many different polynomials that are equivalent to each other. We know that they are equivalent to each other, but the neural network doesn't really know that these are equivalent to each other. So you need to basically put these symmetries in the architecture of the neural network. Okay, so the first symmetry that we took into account is basically the orderless symmetry. So you have these lemmas that you have and that you have proven, and basically it doesn't really matter the order at which you have proven them, as long as you have proven the same ones, basically. So basically you need the Q-value function has to be basically invariant to these to permutations of these elements in the memory. Okay. The first symmetry. The second symmetry, and this is the most important one, is actually like invariance to variable relabeling. So if you have a function and you change all the variable names consistently across the objective function and the constraints and everything, then you have obviously the same exact problem, right? You have the system of equations or the same optimization problem. So that's exactly what we call invariance to variable relabeling. Now, for the network, he can treat it basically as different instances, but that's actually very inefficient, and that can lead to very slow learning, basically. So we took into account the fact that if you apply permutation to all the elements in the memory that you have, and the function that you want to prove, and the action, then you have to have basically the same Q-value function exactly. Okay. Okay, so now the baseline to this, so we have this dynamic proof, which basically uses machine learning in order to find this, to guide the search space, basically, and we compare this with basically what's existing in the literature, which is what's called static or non-compositional proofs. And these basically correspond to basically unrolling your inference rules for a fixed number of steps and then solving a convex optimization problem to try to find a proof. If you don't find a proof, you basically go to the next level and so on and so forth. Okay. Okay, so let's go a bit more into detail about this. So if you compose basically your inference rules for a fixed number of times, so for example L times here, then you get always functions of this form. Okay, if your problem is like this, okay, and then you compose them in the ways that I described before, you always, like with additions and multiplications, then you're going to always get functions that have this form here. Okay, and basically L here is the number of times you unroll the inference rule. So if you unroll the inference rule just one time, you'll get basically a few functions. If you unroll them again, you'll get more functions and so on and so forth. Okay. So obviously when you unroll more and more, you get more and more expressive functions, obviously. So the static proof consists in basically trying to solve the optimization problem, which consists in finding these lambda alphas for L is equal to 1, which is basically the first level of the hierarchy, which corresponds to just unrolling once. If you don't get a proof, then you go to the next level and so on. Okay, and from the completeness of this proof system, you will eventually get for a finite L a proof. But the problem, however, is that this L can be actually very large. So this L can be actually much larger than the degree of the polynomial that you want to prove. Okay. So, for example, if we take again the same example as we took before in terms of the stable set, if you want to prove that 1 minus sum of x i's is non-negative, just like we did in a dynamic way, you actually need to do the product of all the different 1 minus x i's. So you really need to go to the nth level of the hierarchy, okay, in order to prove something about a polynomial that is just of degree 1, okay. And the problem is that the nth level of the hierarchy is just a very, very large search space, and you cannot just afford to solve a linear optimization problem on this very large search space. Okay. So just maybe to highlight pictorially more, So this is the, like, you start with the first level of the hierarchy in the static way. In the static proof, you start with the first level of the hierarchy and you want to prove that this polynomial P is non-negative. P does not belong to the first level of the hierarchy, so you go to the second one, it doesn't belong, you go to the third one, it doesn't belong, and so on. Instead, the dynamic proof, what you do is basically you start from these axioms, and then from the axioms you're going to derive very specific polynomials that can belong to very high levels of the hierarchy, but that's fine. You're not going to consider the full space anyway. Okay, this is going to be guided through this machine learning procedure. Okay, till basically you arrive to this final polynomial. So in a way, the dynamic proof is more guided and does not basically, enumerate all the possible functions at a certain level. Okay, so the experimental setup that we considered is basically we trained on random graphs of 25 nodes and hundreds of edges. So we considered like quite dense graphs. Okay. Because these are the graphs where it's actually more difficult to find to solve the independent set problem or the stable set problem, and then we tested it on graphs where the number of nodes is around 50 and you have thousands of edges, and so we set the episode length to 100, and again there is no ground truth or prior proofs at all. So this thing is completely unsupervised, and the idea is to try to see how this dynamic and static approach basically differ to each other, and whether we can use machine learning in order to guide which functions to take from higher levels of the hierarchy, basically, without taking the full thing. Okay. So this is basically the output of the agent when you query it on the complete graph of size 7. Then you get basically what's expected, in the sense that you start with this polynomial 1 minus x7, 1 minus x3 minus x7 is non-negative, and then you basically multiply it by 1 minus x6 to get a new polynomial that is non-negative, and then you multiply it again by 1 minus x4, and you do it basically sequential until you get that 1 minus sum of xi is non-negative, which is really the human proof of, or the proof that one would expect basically from using this proof system. Well, in the cyclic graph, you can also try to follow the proof, and it's a bit more complicated, but eventually it tries to understand this parity problem and really manages to prove that the upper bound is 3 and not 3.5. And on random graphs, this is an example. So numerically, this is basically a comparison of the performance that we have on with the dynamic proof, with basically the dynamic proof system using this agent. This is the upper bound, so the lower the better. That's basically the side of the graph. So that's like when we're 50, we have around maybe 1,000 edges or so, and we compare basically with what the upper bound that you would get using the static hierarchy. So the static hierarchy, it's actually not bad, in the sense that if we go to higher enough levels of the hierarchy, we'll actually be able to get the optimal solution provably. But it's just that if, when we go to the 5th level of the hierarchy, for example, it's not enough to actually get the optimal stable set, the optimal cardinality of the largest stable set. In terms of what's interesting to see here is basically in terms of the size of the linear program, what you need to solve as a linear program is much smaller for the dynamic proof than for the static one, because for the static one, you need to enumerate everything. So you need to solve linear programs of size 1 million, for example, whereas for the dynamic case, you just need to solve a linear program which has basically which has a number which scales basically just as the number of elements that you have in your memory, which is set here to 200. Okay. Okay, so this really highlights the benefits that the dynamic proof can offer with respect to static proofs. So these are the conclusions, more details in the paper, but I just want to end with some of the lessons that I took from basically this project. and what are the difficulties basically in the emerging field of using machine learning for mathematics. So one of the, I think the main difficulty is really data generation. So I think one of the really cool things about perceptual tasks is that data is very abundant, so you can really have very good quality data. In mathematics, you can obviously always try to generate synthetic data, but these data will not be as good as what you get naturally. So there is always this very hard transition from synthetic to real theorems or real like inequalities and so on and so forth. So data generation is one very important problem. One other problem is that your rewards are extremely sparse. Usually, like proofs are long. So we circumvented this by basically using the structure of the inequalities that we have by giving a reward at each step. There are many symmetries in mathematics, and we need to really take this into account in the architecture. Otherwise, it will just not work at all. That's my or like it will be extremely inefficient. Basically, it will really start being learning anything, but like after a very long time. And the last thing is that you have very large action spaces, basically. So in this case, for example, we had action spaces which are quadratic, basically, in terms of the number of elements in the memory. So that's yeah, it can go very quickly, very large. So that's one of the big problems and one of the big challenges we need to address in the field of machine learning for mathematics. So I'll end here, and if you have any questions, please let me know. Thank you.